This is a series of YouTube videos that show how you can program a microcontroller at the register level. If you find these nutshells useful, please support the channel by liking the videos and subscribing. Your support helps create more content like this, and you'll stay updated with new tutorials and insights. This nutshell looks at the overview of the course, the equipment used, the ATmega2560, and the teaching boards. The series of YouTube videos are based on a university course in microcontroller register level programming and is suitable for both students and home hobbyists. The microcontroller used is the Microchip AVR ATmega2560. However, the techniques shown in the course can be applied to other microcontrollers. The videos are condensed into nutshells that show how the microcontroller onboard devices can be programmed. The nutshells are divided into an introduction to microcontrollers. We look at C programming, including program development, the C language, and bit masking. And we look at onboard devices, the GPIO for the digital interface, the ADC to read an analog voltage, the AC to compare two analog voltages, three serial interfaces, the USART, SPI, and TWI. We look at interrupts, including internal and external interrupts. We look at timers, including real-time interrupts, waveform generation, period and frequency measurement, and finally we look at some CPU registers that can be used to program the EEPROM, sleep modes, and the watchdog timer. The equipment that I use in the nutshell coding examples is the free AVR Microchip Studio and the seaRidge Mega Pro teaching board. You can see here a picture of the Microchip Studio. It's an integrated development environment which includes an editor allowing you to type in the C code, a compiler which converts the program into machine code, a downloader to program the machine code into the microcontroller, and a debugger when you can run and test the code. The seaRidge Mega Pro board shown here has a ATmega2560 microcontroller with a range of external devices connected to the onboard devices inside the chip. Visually, we can see some of these external devices, including a color display, two hex display drivers, we have switches and buttons, we have LEDs, we have two variable resistors, a rotary encoder, a servo motor, a fan for PWM, a PIR sensor, and a USB interface. Finally, we can see examples of the C code written for the onboard devices running on the seaRidge Mega Pro board. I will show examples of the code written in the Microchip Studio. Then I will download the code to the Mega Pro board and run it to observe its behaviors. If we look here, we can see here is a live video of the Mega Pro board. I am running some test software. I can use this to test the ADC switches, LEDs, PWM, UART, etc. So we can observe the behavior. In this example, I'm going to look at the ADC, and then I can look at the pots. So pot 1 is up here, and we can see pot 1 variable changing. Similarly, we can look at pot 2 and see that variable changing as well. So we can look at the code and see it running on the microboard. The ATmega2560 can be broken down into two parts. The first part is the CPU and memory. The second part is the onboard devices. The AVR uses a RISC processor with 135 machine code instructions and 3 memory systems. There's 256K flash for program storage, 4K EEPROM for semi-permanent storage, and 8K SRAM for variables used by the program. The microcontroller has a JTAG interface used to program the microcontroller and debug the code. And the clock frequency ranges from 0 Hz up to 8 MHz at 2.7 volts, 16 MHz at 4.5 volts. It comes in a 100-pin device that can be thin quad flat package or a ceramic ball grid array. The ATmega2560 onboard devices are used to monitor and control external sensors and actuators or communicate to intelligent devices. The general purpose input-output is a digital interface that is either on or off, such as a switch or a LED. The interface is grouped into 8 lines called a port. There are 86 GPIO lines grouped into 11 ports, port A through to port L. Note, there is no port I. The analog to digital converter converts an analog voltage input into a binary number that represents the size of the voltage. There are 16 multiplexed analog inputs feeding into one 10-bit ADC, allowing one analog input to be read at one time. There is one analog comparator used to compare the voltage levels of 2 analog inputs and will give a digital output depending on which input is higher or lower. The serial communication system converts parallel data into a serial form that can be sent down one line. The ATmega2560 supports 3 types of serial interfaces. It has 4 universal synchronous and asynchronous receiver transmitters, 1 serial peripheral interface, and 1 two-wire interface, otherwise known as I2C. There are 2 8-bit timers and 4 16-bit timers, which are used to generate real-time interrupts, square waves, pulse width modulation, and measure period and frequency. And finally, there are 32 external interrupt lines, which will generate an interrupt if a change occurs on the pin. The interrupt will cause the microcontroller to perform an interrupt service routine and service the external device. Because we are programming at the register level, we do need to look at registers and understand what they are. So a register is a specialized storage location in memory within the CPU, and each register has a unique purpose. They can be categorized into general purpose registers, which are used by the CPU, and special function registers, which are used by the CPU or by the programmer to control the onboard peripheral. They can be broken down into control registers, status registers, and data registers. And here we have an example of the ADC control and status register. It's combined control and status. We can see control here, turn the ADC on, start the conversion, or status, showing you interrupt flags. So this is what you would be programming when you are programming the ADC. The board used in demonstrating programming techniques and how the program works is the seaRidge Mega Pro board. This was developed by seaRidge to aid in teaching microcontroller programming to university, polytechnic students, and home hobbyists. The board has external circuits that connect to the onboard systems such as the GPIO, ADC, USART, timers, SPI, TWI, and interrupts. We can see a picture of the board with some of the external devices shown, including a color display, switches and buttons, 2 hex display drivers, a frequency generator, 2 variable resistors, an encoder, a servo motor, fan and light controlled by PWM. We have a PIR sensor, and we have a USB interface to allow the microcontroller to communicate to a PC. Here we can see a block diagram of the different functions. So we have general purpose input output, SPI, timers, TWI, USARTs, interrupts, and we can see what they are interfaced to. A smaller version of the seaRidge Mega Pro board is the Mega Lite board. This just has less external systems. We still have the color display, the switches and buttons, the hex display drivers, frequency generator, 1 variable resistor, an encoder. We have buses, PI sensors, and the USART. But we don't have the same features. For instance, we don't have the servo motor, and we don't have the fan that the Mega Pro board has. It's still a useful board to have.